All right. Well, now we're going to look at this problem, the finite well problem, quantitatively and see if we can solve Schrodinger's equation for this system. Now, this is a little bit more complicated. In fact, this is one of the most complicated problems that we're going to actually solve completely. Okay. So, hang on to your hat and all of that. But also, I don't want you to get overwhelmed by it. Keep an eye on basically the techniques that we're using. Which will be solving Schrodinger's equation in different regions and then matching them up at the boundaries, okay? That's a very general technique that's going to be valuable to us. And the other thing you can see is what kind of problems you might be solving in the advanced quantum mechanics class, since this same problem gets treated there as well. All right, hang on, and let's take a look. Very good. So we're talking about the finite well problem. And let's set it up so that we can solve it. First of all, the height of the finite well potential looks like this. We're going to make the dimension, the width of the well, L, and the height of the well, U0. But we're going to do one thing differently. We'll set up our coordinate system so that x equals 0 is in the center of the well. In that case, the right edge of the well is at L over 2, and the left edge is at minus L over 2. And we have a reason for doing that. It just makes the solution more convenient because it makes the problem symmetric about x equals 0. And you'll see that that's a tool that we can use when we look for the solutions. Okay? Very good. Now the potential, so the potential for the well then is as follows: U of x is equal to 0 inside of the well. And it's going to be a constant value, U0, outside of the well. Okay, just as we expect. And it'll be helpful to separate the problem into 3 regions, as I've done here: region 1, region 2, and region 3. All right? And now our goal is going to be to solve Schrodinger's equation in each of those regions and then to match up the solutions at the boundaries. And you'll see that the first step is not very hard because we've actually solved the problem already. Okay, but let's go through it. So we'll just start by writing down Schrodinger equation again, the time-independent Schrodinger equation. So we have minus h bar squared over 2m times second spatial derivative of psi is equal to e minus u of x times psi. So here, let's focus on region 2 first, okay? In region 2, u of x is equal to 0. And so we have minus h bar squared over 2m times psi double prime is equal to e times psi of x. Okay, and we can see that the that this can be solved by a free particle wave function, because the wave function looks like the equation looks like this: psi double prime is equal to minus 2me over h bar squared times psi. And then you can see that this can be solved if psi is a sinusoidal function or a cosine function or a complex exponential, which is sort of built out of sine and cosine functions. In fact, the most general solution looks like this. So psi in region 2 could be a combination of sine and cosine functions. Okay, but if we substitute this into the equation, what we'll find is that k has to be equal to the square root of this term here, okay? So we'll find that K must be equal to square root of 2me over h bar, something we've seen before. Just put a box around that so that we remember it. Excuse me. There we are, okay? Okay, now let's take a look at region 3. Remember, in region 3, that's this region over here. And something to realize, for energies at which the particle is bound, the energy will be less than U0. Okay? So now when we write down Schrodinger's equation, it will look like this. Excuse me? It will look like minus h bar squared over 2m psi double prime is equal to E minus U0 psi, okay? But E will be less than U0. So this term is actually a negative quantity. And it's helpful to rewrite that, to flip it around and bring out the negative sign to make it explicit. Let's do that. So we'll write this as minus U0 minus E, because then the term in the parentheses is positive. And now you can see that we have negative signs on both sides of the equation. We can cancel that out. And we're left with psi double prime is equal to h bar, is equal to 2m u naught minus E over h bar squared times psi. Okay, very good. Now, an equation like this, where the second derivative of our function is equal to the function itself, but times a positive number, that can be solved by an exponential function, not a sine or cosine, but by an exponential function where the exponent is a real number. That is, psi of x can be written as I have my reason for using these particular letters. D times e to the minus alpha x plus f times e to the plus alpha x, okay? Where alpha is clearly square root of 2m u naught minus E divided by h bar. If you're going to do it, try once more. I really like this automatic square function, but there we are, perfect. My beautiful square. Okay, so now we found the general form of the wave function in region 2. I'm sorry, in region 3. And the last place is to find it is in region 1. And you can see that that case is very similar to the one that we've just talked about. And in fact, I won't go through it. I'll just write the answer down. Not B. We've already used B. Let's use G, e to the minus alpha x. Okay. All right, I'm just going to leave it. Okay, so we've accomplished our first goal. We've written down the general form of the wave function in each of the 3 regions, region 1, region 2, and region 3. And now we're going to use the boundary conditions on the wave function to figure out what these coefficients are, okay? To figure out what the precise form of the specific form of the wave function actually is. okay? So let's think about what the boundary conditions are. So the first boundary condition that I would like to, that I'll bring in is that if the particle is actually bound, then the wave function should decay on the right side. And in particular, if we go to x equals plus infinity, we should find that the wave function has decayed away to nothing, okay? So the first boundary condition I'll say is that in the is that psi of x has to go to 0 as x goes to positive infinity. Okay? Seems reasonable enough if the particle is bound, but that has a meaning. It means that if we look at the form of the wave function in region 3, here it is, it means that this term must vanish because this term would blow up as x goes to infinity. And since that's not allowed, that must mean that f is 0, that term actually doesn't contribute to the solution of this problem, even though it does solve Schrodinger's equation, okay? Likewise, the second boundary condition will be that psi of x should go to 0 as x goes to negative infinity. The same thing is true on the other side, okay? Think for a second what that means. So that tells us something about the wave function in region 1. So looking at these terms here, you can see that one of them will blow up when x goes to minus infinity. Can you see which one? Okay, it's the second term. So because we can't allow that to happen, it must be the case that g is equal to 0. And we can drop the second term, okay? Okay. Now we have two more boundary conditions that we're going to need to use. Okay, and I'll just write them down here. Well, there are actually several more boundary conditions. We won't end up using all of them. But one of them is that the wave function has to be continuous at the right and left edges of the well. So that means that the solution in region 1 at x equals minus L over 2, that's the right edge of the well, must equal the solution at for region 2 at the same position. Okay? In addition, the first derivative of the wave function at that position must be continuous.
I'm not sure I understand.
Well, then you should pay more attention, Siri. There we go. 1 second. Okay, now likewise, we have the same condition at the right-hand side of the well, and that's fine. That's two more boundary conditions. But you'll see that, in fact, in this problem, we only need 4. We only need one of the edges. We don't need to actually include both. A simplification that comes up because the problem is symmetric about x equals 0. Here, let's pause for a second. Very good. So actually, let's just restate our problem then. So after imposing those boundary conditions at plus and minus infinity, what we're left with is the following. In region 1, the wave function is a decaying exponential, but we'll write it a e to the plus alpha x because it's decaying as we go to negative values of x. In region 2, the wave function has is an oscillating function, and we'll represent it as a sum of sine and cosine functions. And then in region 3, the wave function once again is decaying exponential. Okay? And we remember, we know what alpha and k are. We wrote them down a moment ago. So now the next step is to impose these last two boundary conditions and figure out some solutions. Okay? And as I said, we only need two of these because we're going to use the symmetry of the problem. The fact that u of x is symmetric about x equals 0 because of the way we set that up. Let me describe what that means. So whenever we can use symmetry to help solve a problem in physics, we should do that, okay? And this is the case. In this case, because the problem is symmetric, we know that the wave functions that we're going to get are also going to have some symmetry. In fact, they're either going to be even or odd. And the reason for that is the following. Because the potential is symmetric, that means that the probability density must also be symmetric. Since the system, it looks exactly the same on the left side and the right side, it wouldn't make sense for the probability density to look different on the left side or the right side. Therefore, psi of x itself must be either even or odd. And by even here, I mean that psi of x either equals minus psi of x, I'm sorry, psi of x equals either psi of minus x, and that's called even parity, or psi of x equals minus psi of minus x, and that's called odd parity, okay? And if you go back a moment ago when we sketched out what we thought the wave function should look like, here we are. You can see that the different states that we drew, the different wave functions that we drew, just based on guesses, either have even symmetry, like the first one, or they have odd symmetry, like the second one. Okay? So when we solve this problem now, we're going to assume that the solution has either even symmetry or odd symmetry. We'll actually look for those solutions separately. I know it sounds complicated, but it actually makes the problem a lot easier, which is why we're doing it this way. You don't have to do it this way, but if you want us to be clever and avoid some work, you do. Let's go back down to where we were. There we are. Okay, so now this is the problem that we're going to solve.